with 4 papers. Whoa, and I'm live. I don't need the mic, but they need it to record. Hi, I'm Tom Ball from Microsoft Research. I'll be your session chair. We have 4 papers on temporal properties and automata. And Arthur will take it away with this talk.
Thanks a lot. So hi, everybody. My name is Arthur, and today I'm going to be talking about, the mic is not working? OK, great. Is it good now? OK, good. So yeah, I was saying today I'm going to be talking about coinductive proofs for temporal hyperproperties, and this is joint work with Professor Bernd Finkbeiner. And before I present to you the contribution of this paper, I'd like to talk a little bit about the task of specifying programs. So if we want to specify programs, one way to go about it is to focus on what is it that the program should compute. Examples of such specifications are, for example, P should compute the factorial of its input, or P terminates. Now, this is not always enough. Sometimes we don't care about what the program computes. We don't even care whether it computes something meaningful at all, but we're more worried about how is it that the program is computing. Example of such specifications are, for instance, P is deterministic or P does not leak private data. So if we want to specify what to compute, it generally suffices to consider each execution of my program individually. As an example, if we want to specify termination, it suffices to look at each execution of my program and state that each of them is finite. Now, if we want to specify how to compute, looking at executions individually is not enough. What we need is we need to compare multiple executions. We need something a little more general. And as an example, if you want to formally specify the notion of determinism, one way to do it is to say, give me 2 arbitrary executions of my program P that are sharing the same inputs, and you should prove that they also have the same outputs. This is a relational property. So hyperproperties are exactly the framework that allow us to do that. And they have many applications, in particular to security. OK. So in the context of this talk, I'm not only going to talk about hyperproperties, but I'm more specifically going to talk about hyperproperties of reactive systems, which are programs with the following features. So I would like input and output. I want non-termination. So I'd like to talk about programs that run forever. And I would like to have non-determinism. So those are very interesting features, in particular if you want to model applications like UIs, web servers, operating systems, which are all applications for which security requirements are very important, in particular security requirements that can only be expressed as hyperproperties. OK, so one little remark about such systems is that in this context, executions are infinite sequence of input-output events. So we'll need specific machinery to specify relations between infinite sequence of events. And usually such specifications require the ability to universally and existentially quantify on traces. So this is going to be a critical feature. OK, so let's look at a little example. We have a small program that runs forever, fetches user input, and adds some non-deterministically determined value to it, and then output the result of the sum. And I claim that this program doesn't reveal the exact value of the input through its outputs. And the way we would formally specify that is we start by fixing some dummy value lambda. And what we're going to say is, for all trace of this program, there should exist a trace where we have fixed the inputs to be the predefined constant lambda, and yet the outputs are indistinguishable in between the 2 executions. So if we think a little bit about it, what this specification means is that the effect of the input of an arbitrary input is indistinguishable from the effect of the specific input lambda. And therefore, from the point of view of an observer of the system, we can't really infer anything meaningful about the inputs just by looking at the outputs. OK, so just as a remark, we have quantifier alternation in this specification. And we have here the temporal modality globally. And we need that to be able to inspect the content of the execution over time. All right. So this is all very nice. We have a framework for specifying hyperproperties of reactive system. But now how do we prove them? And I have bad news for you. So it turns out that such for all exist temporal hyperproperties are very difficult to verify, and even more so if you want a fully automated approach. And unfortunately, there is still no clear interactive proof technique targeting such hyperproperties. So automation is still relatively out of reach, and interactive proofs are or deserve a little more exploration. So what are the challenges? Why is it so difficult? So if we take a step back and look at the general problem we're looking at proving statement of the following form. For all trace tau1, there exists a trace tau2 such that the two traces together satisfy some relation that is our specification. Now, if we want to do a direct proof of this statement, the first thing we need to do is to explain how we instantiate the innermost existential quantification. So typically, in a constructive setting, we do that by giving a Skolem function that is producing some execution based on some input trace. So once we have done that, which, by the way, might be a very complicated task, like specifying such an object as a function that reasons about infinite sequence of events is not necessarily trivial. But once we have done that, there is a second step. We need to show that it produces feasible executions, feasible traces. So that's the second step. Might also be complicated to prove. And once we have done that, there is still a third step. We need to prove that the trace produced by our function are actually compatible with the specification. Okay. So this is a very tedious and time-consuming process. And in particular, if we made a mistake if we make a mistake in the beginning, if we have a wrong choice of a function f in the beginning of the proof, this mistake can only be revealed at a later point. So for example, it could be revealed very late in the process of step 2 or very late after step 3. And this is not very desirable. It's going to be difficult to do a direct proof in that way. So instead, what we would like to have is a more incremental proof technique. And by that, I mean that we would like to progressively construct the witness for the existential quantifier and simultaneously prove that it's a suitable witness as we go. And another aspect is that we would like a local proof technique. And by that, I mean that reasoning about objects like big object like infinite sequence of events is complicated and not very intuitive. Instead, we would like to reason about much smaller objects like state and events. So the contribution we present in the paper is exactly going in that direction. What we're proposing is we're presenting HyCo, which is a framework for deductive proofs of all exist temporal hyperproperties. It is mechanized in the Coq proof assistant, and it has support for incremental proofs via parameterized coinduction. Okay. So let's give a quick tour of HyCo's core. So at the very core of HyCo, we talk about labeled transition system. So we have a set of state, S, and a set of events, E, and a transition relation that explains how to move from state to state. Maybe we have some initial state I. Okay, so very general setting. And specifications are going to be expressed as relations between infinite sequence of such events. So again, very general. We're not making any assumption about how the specification are expressed. We just take arbitrary relation between a sequence of events. And now how do we connect systems and specifications? We do that by introducing proof quadruples. So how are they looking like? So in the middle, we have two states. So on the left-hand side, it's going to be a state that belongs to an execution that is universally quantified. On the right-hand side, we have a state that belongs to an execution that is existentially quantified. And at the very right of the quadruple, we have a trace relation, or little specification here. And the important thing is what is on the very left. It's a context that consists of a state relation. So it can also be viewed as a set of pair of states. And if I want to be a little more precise, actually, there are two kinds of quadruples because the context is controlled by guards. So the first kind of quadruple is telling you that the context is protected by a guard, and this is represented by this solid box around it. And the second kind of quadruple is telling you that the context can be used in the proof, and this is represented with this dashed box. Okay. So something important to notice is that the definition of those quadruple is coinductive. And in particular, the definition of the dashed one depends on the definition of the guarded one and vice versa. So it's a cyclic definition. Okay. So I'm not going to present the definition, the exact definition, because that would be very long and boring. Instead, I'd like to explain how the system can be used for the specific case of relational invariance. So I'm going to focus for a bit on specification that can be expressed as globally some relation between events should hold. And we're going to look for a bit at the proof rules for this specific case. OK. So the first rule, the most important one, is actually the soundness theorem of the framework. What it says is that if you want to prove that a transition system satisfies a property of the form for all exists globally phi, then it suffices to show that initial state of the system are related by a quadruple with an empty context. So that's the first thing. Now, how do we actually prove such quadruples? So the main rule is the step rule. And what it says is that if you're focusing on two states, S1 and S2, what you have to show is that for all way to transition out of S1, there is a way to transition out of S2 such that the events emitted by those transitions are satisfying the relation. And then the targeted states are, again, related by a quadruple. Now, the important point is that the context is released, the guard around the context is released when we are making a step. So now the question is, how do we make use of the context? And the two following rules are explaining us exactly how to do that. So the invariant rule is explaining to us how we add things to the context. And what it tells us is that at any point in time during a proof, you can extend your context with a relation H prime that contains the current state you're looking at. And the cost to pay to be able to extend the context is that the proof resumes with not S1 and S2, but arbitrary S1, S2 in the new relation that you added to the context. OK. Another very important note is that contrary to the step rule, the guard is not released by the application of the invariant rule. Otherwise, we would be unsound. OK, and now the final rule is making use of the context. And what it tells us is that whenever the context is not guarded, we can use it to discard the current proof tree. To close the current proof tree. So it suffices to show that the current states are in H if H is unguarded. All right. Perfect. OK. So I just want to make the point that this satisfies our original goal. It's a local proof technique because we only refer to state and events, and incremental reasoning is achieved with the invariant rule. So unfortunately, because of time reason, I cannot explain to you how to use those rules on a concrete example, because this would be a little bit too long. But I want to make the point that this also applies to more than just globally phi. Actually, it applies to arbitrary safety relation via the notion of property derivative. I think there is a talk about that in the session, actually. But so yeah. And as a corollary, you can also derive some useful rules for other temporal modalities, like, for example, weak-until or the next modality. It also applies to programs written in a programming language. So if you give me a small step operational semantic of your programming language, you can instantiate the framework and derive some very nice syntactic rules to reason about your programs. And it also generalized to for all star exist star. So I only talked about the specific case where you have one universal quantifier and one existential quantifier, but it also works for n universal quantifiers followed by m existential quantifiers. And it generalizes in a very natural way. OK, so what about limitations and future work? So completeness. We proved soundness, but the system is incomplete. There are very easy counterexamples to that. And of course, it would be nice to have completeness. But my intuition, having worked on this for a long while, is that it's not possible to reach completeness if we want to preserve as much incrementality and as much locality. Or at least it's very difficult. It's not clear to me how to achieve that yet. One research direction is to look at prophecy variables, which would be a way to make the system more complete, but I'm not sure that it's enough to be really complete. OK, another interesting question is non-constructive aspects. So it turns out that the soundness proof of this logic is non-trivial, and in particular, it requires a relatively subtle use of the axiom of choice. Now, the natural question is, can we drop this? And the answer is no, we cannot. I have formally proven that. Another interesting research direction is probabilistic treatment of the existential quantification. So this framework focuses on properties of the form for all exist, but in some cases, we not only care about existence, we care about existence with a high probability. So this would be very interesting to look at. And last, combining this framework with separation logic in the style of simularis, for example, would be very interesting. And in particular, it would allow us to leverage the very nice reasoning principle of separation logic to specify heap manipulating programs. All right. So if you want to know more, want to learn how to use this system, look at example, look at the proof of soundness, all the details are in the paper. The Coq formalization of the whole system is also available on my GitHub, so please have a look if you're interested. And otherwise, I'll be around for any question.
Great, thank you. Thank you very much, Arthur. We have 5 minutes for questions, and please raise your hand, and we'll get you a mic.
Yeah, so I have 2 questions. So for finite cyclic structures, we know that for all exist box hyperproperties, you have completeness with a finite number of prophecies. So
yes.
What's different in this setting? And the second question is, okay, I'll ask the second question after.
Yes, so that's a very valid point. The problem is, I think you're referring to a paper that says that you can add prophecy variables and then you recover completeness, but the problem is that then the property that you have to prove is no longer a safety property. And I think you cannot prove it by coinduction only. You need something a little more specific. So I'm working on extension that would support that, but it's very non-trivial.
Yes, it's not safe.
Yes.
They're not safety properties. They're local to each trace, but they're not safety. Yes.
Yeah, exactly.
Okay, and the second question is, since you're going to an interactive proof system, why to restrict yourself to synchronous hyperlogic instead of an asynchronous one?
That's a very good question. So for the purpose of this talk, I acted as if everything was synchronous. Actually, you can very much deal with non-synchronous systems. This works equally well. Yes, and there are various ways to actually weaken the underlying coinductive relation so that you have very nice reasoning principle in the case of asynchronicity.
Thanks.
Okay, thank you. We have another question over here.
Yes, thank you. I had 2 questions, but I think you answered one of them, so I will answer the other. This Harvard example you had in the beginning,
yes.
How should I think of that? Is that like plain non-deterministic choice? Like, are you proving there exists a non-deterministic choice that makes it work?
Yes.
Because that sounds like something that's not preserved under refinement, where I can make concrete the choice. And then if this is a security property that relied on all the non-deterministic choices being realizable, and then I refine it with an implementation that always makes a concrete choice, now I lost my non-interference or something like that. So is this just out of scope, or like what is? I'm not sure
it's not out of scope. So it's just. So I think one way to understand it is that there are many examples where you could specify the usual notion of non-interference, and it's a for all hyperproperty. But this is way too strong a requirement. You cannot even prove it, and yet you have the intuition that there is something that cannot be leaked. So the whole point of having this style of existential quantification is to weaken specification and still be able to prove something meaningful about program. So arguably, I agree with you that it weakens drastically the specification, but it allows you to specify things that otherwise would not be provably non-interferent. So it is still very useful in that sense. And I think it also connects to the comment I made about probabilistic treatment of existential quantification, where we probably want something a little bit stronger, where you say, okay, there is a very high probability that things work out. So just very quickly, another way to look at it is that this existential quantification, in a security context, this existential quantifier can be interpreted as there exists a way to confuse an ill-intentioned observer of the system, essentially. So I don't know if it answers your question completely, but yeah, we can.
Any other questions? I have one question. Why don't we let the next speaker get set up? I'll ask. So my last question is about incrementality, and is that related to derivatives? The use of derivatives, where does it come from?
It does not. So not directly, actually. So derivatives are used so that you can actually reformulate the problem of proving the hyperproperty as a coinduction question. So in that sense, derivative play a role. But incrementality is really about doing the proof itself by accumulating knowledge while you're stepping through the execution of the program. So it is not. It has a link, but yeah, okay. not directly.
Okay.